let's discuss our next topic on non-inertial reference frames and apparent forces. So under that we will discuss centripetal acceleration and centrifugal force. This will be our lecture 2. So as mentioned in the lecture 1, so the content of this slide is taken from this reference, Introduction to Dynamic Meteorology, 5th edition, by James R. Holden and Gregory J. Hacken. So let's discuss the frames of reference. So what do you mean by frame of reference? So how many types are there? We shall discuss now. So this is, let us consider our Earth system and the coordinates x, y, and z. So this is a particle. Let us assume indicated with the letter P here. So this pink colored arrow represents the distance of the point P from the origin. So here let us assume that the coordinates are fixed in space here, or with respect to this Earth system here. So now, according to Newton's laws of motion, any mass in uniform motion with respect to a coordinate system which is fixed in space, means which is not rotating, which is fixed in space, will remain in uniform motion, and such motion you will call it as inertial motion. And the frame of reference, we call it as the inertial frame of reference, or even the absolute frame of reference. So what do we notice in inertial frame of reference? So there will not be any force acting on the particle, and hence the acceleration is 0. So that's why we have written here, so force acting on the particle is 0 and hence acceleration is 0. In case of non-inertial frame of reference, even the real forces acting on the particle is 0, but you do find that the acceleration is not 0. So the reason is, in a rotating coordinate system, you find the apparent forces being acting on the particle. So that is why we call this as a non-inertial frame of reference, and whatever this forces which are acting on the particle, you call it as pseudo force or the apparent forces, we can say. So let us discuss now the geocentric reference frame. So the geocentric reference frame is a non-inertial frame of reference. So Newton's laws of motion can only be applied such a frame if the acceleration of the coordinates is also taken into account. Meaning that for a geocentric frame of reference, if you take, we have to consider the acceleration of these coordinates, meaning the coordinates move along with the rotation of the Earth. So these effects can be included by introducing the apparent forces in the statement of Newton's second law. So for a coordinate system with a uniform rotation, if you assume, so two such forces we can call it as the centrifugal force and the Coriolis force. So let us discuss about centripetal acceleration and centrifugal force. If you notice this diagram, so where if it is assumed that a ball of mass m is being attached to a string and made to whirl through a circle of radius r. When it is whirled through a circle of radius r, it is with a constant angular velocity omega. So from the point of view of observer, the ball will be moving with a constant speed, but the direction is changing, and hence the velocity is not constant, meaning that after a time t, the change in velocity is represented by v plus delta v, where the ball rotates through an angle delta t also during this time. So now we will try to compute the centripetal acceleration, which we call it as an inward acting force and centrifugal force as outward acting force. So now from the diagram, so because delta theta is also the angle between v and v plus delta v, so we can write the magnitude of delta v as delta v is equal to mod v delta theta. So that is how we can obtain the magnitude delta v with respect to magnitude of v and delta theta. So what we do is now, to obtain acceleration, we divide this equation by delta t, and we will take the limit delta t tends to 0. So finally we obtain the dv by dt, which is equivalent to mod v. This delta theta by delta t gives you d theta by theta dt multiplied by position vector r by the radius of this circle. Since it's an inward acting force, we consider dv by dt is equal to minus omega r. So as we know, the velocity is given by the angular velocity times the radius, and d theta by dt, which is nothing but the angular velocity. So we can define the centripetal acceleration as the square of the angular velocity times the axis times the distance from the axis of rotation. So I repeat, the centripetal acceleration is square of the angular velocity times the distance from the axis of rotation. So this centripetal acceleration is due to the force of the string pulling the ball. Okay, it means, so when it actually moves in this direction, there exists a force of the string which is pulling the ball towards the center. So let us assume now the ball is rotating along with the coordinate system, or we can say the motion in a coordinate system rotating with the ball. So in this rotating system, the ball is stationary. So a force acting on the ball, namely we call it as a centrifugal force, which just balances the force of the string on the ball. The centrifugal force is equivalent to the inertial reaction of the ball on the string, and just equal and opposite to centripetal acceleration. So in other words, the centrifugal force is equivalent and opposite to the centripetal acceleration. So to summarize the entire concept, observed from a fixed system, okay, the rotating ball undergoes a uniform centripetal acceleration in response of the force exerted by the string. So observed from a rotating system, along with it the ball is stationary and the force exerted by the string is balanced by centrifugal force. Thank you.